All right, for the second video, we're going to start with a definition. We're going to talk about what zeros of a polynomial are and what multiplicities of those zeros mean and look like, right? So we'll start with the definition. Definition. If a polynomial has a factor x minus h to the p. So if there's a factor with a potential exponent, say h is a zero of multiplicity p. All right, so that's double definition. So we've seen this before, right? We just did this with the intercepts. We did a bunch of factoring. So this 0 was 0 of multiplicity 2. This 0 is when x is equal to 1, multiplicity 1. This 0 is x is equal to negative 1, again with multiplicity 1. And over here, right, our zeros were 3, 1, and negative 1. And here they all have multiplicity 1. So let's see what this looks like graphically, okay? Let's give a function, say, look at 3 different roots. We get x minus 1, x plus 2, and let's say x minus 3. All right, and let's give this a multiplicity of 2. Oh, it's going to have an exponent of 2, that factor. Give this one a multiplicity of 3. It's going to have an exponent of 3. Let's look how these different multiplicities and these different roots look. So let's start with this one, the multiplicity of 1. That's right here. Okay? If it has multiplicity 1, it just kind of crosses through the graph. Kind of like normal. Very locally, it kind of looks like a line. Look at this root, x minus 2, or x equals negative 2. There will be a 0 at negative 2 of multiplicity 2. But now it doesn't cross at all, it just touches it. Specifically, it kind of looks like a parabola. Really nearby, right? It kind of looks like a parabola. The 0 has multiplicity 2, and it looks like a parabola. This 0 had multiplicity 1, and it looked like a line. Well, this 0 has multiplicity 3, right? When x is equal to positive 3, the multiplicity is 3. The exponent is the multiplicity. Multiplicity 3, if we kind of zoom in on it, looks like a cubic function, right? X cubed, one of our toolkit functions. That's sort of the behavior for multiplicities. All right, let's make all of these multiplicity 3. All of these multiplicity 3. Oh, look at every time, all of these x-intercepts. If they're all multiplicity 3, they all kind of look like cubic functions nearby. And again, the graph, looks, you make this go up, right? Graph looks really bizarre here. How big does this get? It's up to like 600? Yeah, it gets really big. But what we care about here are the roots, the zeros, the x-intercepts. Because they have multiplicity 3, they all kind of behave like cubic functions here. Let's make all the multiplicities 2. Ooh. We make all the multiplicities 2. Look what happens. All of the x-intercepts, very locally, they just kind of look like little parabolas. Again, if I zoom in on this one, kind of looks like a parabola. If I zoom in on this one, kind of looks like a parabola. If I zoom in on this root, it also kind of looks like a parabola. All right, so that's what we're going to talk about, all right, with multiplicities. So let's get that as a property. Property. The appearance of multiplicities 1, 2, and 3. Okay. If a 0 has a multiplicity graphically, something's going to happen. So if p is equal to 1, it crosses, kind of like a line. So if you have a 0 of multiplicity 1, it sort of is going to look like this. Right? It's just kind of crossing the x-axis. If p is equal to 2, or a bigger even number, it bounces off like a parabola. Again, it's not a coincidence that x squared is a parabola and x to the first power is a line. In this case, we'll get something like this, where the x-intercept bounces off. Here, x-intercept crosses. And again, if p is equal to 3, or a bigger odd number, then it's sort of like it crosses flat, let's say, like a cubic function. All right, in that case, oops, we don't need the y-axis. It would look something like this. So these are the sort of 3 different things for zeros. And again, I mentioned here that if it's a bigger odd number than 3, it still kind of looks the same. Let me show you what I mean by this. Okay. So if I have something like this, I need to reset my zoom. Okay, let's say -5 to 5. Great. Right, multiplicity 3, it kind of tangentially goes through kind of like a cubic. If I had a multiplicity 5, still has the same shape, just flatter. Multiplicity 7, same kind of shape, just even flatter. So the bigger the multiplicity, the flatter it's going to get in general. Same with even ones, right? Multiplicity 2 bounces off like a parabola. Make that a bigger number. The same idea, same shape, just flatter, right? 6, even flatter. 8, even flatter, okay? But it's still bouncing off. Anyway, that's the idea for multiplicities, okay? We're going to do a couple of examples and then move on. So first, I want to look at example 6 in the textbook. Oops, I don't have this section pulled up. We're going to look at a nice graph and see what we can say about that graph. Okay. Example 6 in the section is right here. Use a graph of the function of degree 6. And again, we know it's at minimum degree 6 because it has 1, 2, 3 turning points. Never mind, forget that. To identify the zeros and their possible multiplicities. The zeros are the x-intercepts. Where does it cross the x-axis? Or where does it touch the x-axis? Right? It doesn't cross here. So it's going to happen at -3, -1, and at +4. Okay? So -3, -1, +4 are our zeros here. And then what kind of multiplicities are they going to have? Well, let's look. This one bounces off, kind of like a parabola. That's going to have multiplicity 2, or maybe it's 4, maybe it's 6. It looks kind of like multiplicity 2. It's not super flat. Okay, so this one is multiplicity 2. Look at the next root. What kind of multiplicity is this going to have? It just kind of crosses kind of like a line. That's going to have multiplicity 1. And then the last one behaves kind of like a cubic function, right? It goes very horizontal. And very locally, if we really zoomed in, it would be like a cubic function. So we're going to say that has multiplicity 3. Right? And if you really want to be super clear, you can list the zeros and list the multiplicities and say respectively, which means that this 2 goes with that -3, this 1 goes with that -1, and that 3 goes to 4. A lot of times, I'll be okay if you leave this off, though. All right. That's what we have going here. Then again, we could ask this. This is a graphical way of doing this problem. We could also solve this analytically. We had a different function, like example 3. Find the zeros and their multiplicities. And I'll give you a function this time. In part A, I'll give you f of x equal x squared times x plus 2 cubed times x minus 3 squared. So the zeros are everywhere when the function value, right? Zeros are x-intercept, right? Which is just when y is equal to 0. So it's going to happen right here when x is equal to 0, right here when x is equal to -2, and right here when x is equal to +3. And their multiplicities, well, this one, oh, it has an exponent of 2. It happens twice. This factor, -2, has an exponent of 3, happens 3 times. This one has an exponent of 2, happens twice. So that's the zeros and their respective multiplicities. All right, and that's really it. Okay. But remember that this method only works if it's already factored. So for something like part B, we have f of x is equal to 3x to the 4th plus 6x cubed plus 3x squared. This is not factored yet. So you have to factor first. We can't just say, oh yeah, 0 multiplicity 4, 0 multiplicity 3, 0 multiplicity 2. No. We got to factor it all. So to factor, we always start with the greatest common factor. What's the biggest thing we can pull out? We can pull out a 3. And then they all have x's. Specifically, we can pull out an x squared. This first term, we're just going to be left with an x squared. Second term, it's going to be a 2x. This one's going to be a 1. And we can factor that again. 3x squared is just going to hold tight. Factor this. This is x, what multiplies to 1 that adds to 2, 1 and 1. So it's going to be x plus 1 squared. So our zeros here are 0 with multiplicity 2. And this 0 is -1, again with multiplicity 2. All right, and because both of these have multiplicity 2, it kind of behaves like that parabola. So if we kind of check our answer and go off to a graph, we graph this function, 3x to the 4th plus 6x cubed plus 3x squared. We can really see, right? Both of these zeros are bouncing off right here. Bouncing off right here. That's consistent with our graphical interpretation of what we've got right here. All right, and that's zeros and multiplicities.